we're mainly going to be looking at decorators, metaclasses, and descriptors. And like I say, we're using these in today's talk. And we're aiming this towards if you're building some kind of library or framework. You probably don't want to use these techniques in normal code. They'll either get you great job security or you'll be fired because no one else will be able to understand it. So like I say, Python, and this actually gives us a better understanding of how various features in Python are implemented. So the main principle here is dry, and I'm trying not to talk about the humour in this talk when I say dry, but rather don't repeat yourself. Don't repeat yourself. And third time. So I imagine if you've done programming before, you're familiar with the concept, but just to go over why, it harms your code because it makes it harder to read, slower to write, and it's difficult to modify. I don't know, if I'm, say, adding 1 to a variable in 5 different locations, and all of a sudden I'm told, you should be adding 2 there. I've got 5 points in which to change the code. So we're going to try and avoid repetition as much as possible. So briefly going over some building blocks. If I'm going too slowly, let me know and I'll skip over some of these. So we've got our code, and that's what we're manipulating, but what's it actually made of? Our basic building block is statements. They're the bits that actually do things, and they come in 2 different scopes. You've got global scope, which is the current module we're executing in, or the current Python file, and the local scope, which is the function or class that we're currently in. And now these statements come together to build functions. So we've got functions and classes here, an example of how we're using them briefly. And as you can see, the functions can be inside the classes as well. That's part of the power. So simple function here. We can use arguments either positionally by keyword, and we can supply default values. But we need to be careful with default values. If we see the example here, can anyone work out why we might have the 6 in there as well when we called append 7 and it's supposed to be with an empty array? Yeah?
Sorry. Oh, I thought I knew.
Do you want to take a guess?
Is it because array equals empty array in the parameter doesn't actually rewrite the value of the array?
Yes.
Yeah.
So when you set default arguments, they're set at the time when the function is declared. And because arrays and lists in Python are mutable, if you change the value of the list, it's going to change that actual array there. So next time you call the function, it'll be the new value, which might be powerful. Most of the time it's not what we want, so simple little pattern to work around that. And now we get the intended result. Then some of the things that are newer in Python that we're going to be going over is the slash, just after pos only, specifies that the things that come before it, you cannot pass by keyword. Python will complain if you do. And we've got star args collects up all the arguments past positionally that we've not already collected. Star quargs collects all the keyword arguments up. And you can see an example of how we've called this function at the bottom. Then we also get closures in Python because functions are first-class objects. So we can, like here, pass them around, create them within functions, return them from functions. And you can see here, if we call the add2 create adder with 2, we get our little function to add 2 to an item. And the local variables get captured by the function. If we wanted to say that z can be changed, we have to say it's the z from the outer scope, or because if we leave that out, it'll try to define its own little z within the add function. And then Python goes, you're trying to do z equals z plus 1, but you've not told me what z is, and gets upset. So skipping on to classes. So mostly in Python, they're wrappers around dictionaries, and this is going to be quite helpful to us later in the talk when we want to be able to add things dynamically. So a simple class, we can attach variables to the class itself, or we can create class level variables that will be the same across instances. We've got our instance methods, which, now the thing with instance methods is you see how we call this first parameter self. Well, we don't have to. I think sometimes people in Python see that and think, oh, you must call it self. It's just a parameter. We can call it anything. We could call it this if we want to make our code look more like, say, Java or JavaScript. We could just call it X if we wanted to. I don't recommend it. It's not very clear, but you can. The standard in Python is to call it self. So that way we know what we're looking at. Other Python programmers will know what you're talking about. Then class methods. Typically we'd call the first parameter CLS for class. Again, like self, you don't have to, it's just convention. And then we've got static methods using the static method decorator. And those ones don't take any reference to the class they're currently in or the instance. It's just, I do a brief little thing. I'm related to the class, like here we've got the pass string, but we don't really care about the specifics of what it is.
So it's a Python.
Yes.
Yeah.
And then some methods you'll see are surrounded by a double underscore. We tend to shorten that to dunder because double underscore has loads of syllables. Do we really want to say all that? So this you'd call dunder init, and they let us customize loads of different parts of the class. Then a brief overview of inheritance here, and the most important thing to note is at the bottom there with multiple, that Python lets you inherit from 2 different classes at the same time, and we'll be using this later when we get onto descriptors to be able to define some quite useful behavior. So now, with those fundamentals out of the way, let's get on to the motivating example. We've got our nice little add function here. Maybe we're building a maths library or something, and I don't know, something's not quite working. We want to be able to trace things through. So we add some little print statements to say, well, we're calling the add function with these arguments, and we're returning this result. Great, you say. Now we've got a little subtract function that we want to do the same thing with. And there's a lot of duplicate code there. And now we've got more functions that we need to do. Does anyone else really want to be adding those print statements to every single function manually? And then, when you no longer need them, go through and remove them all manually? I know I certainly wouldn't. So this is where we introduce decorators. So this bit is, I think, where we'll switch over to the live coding demo. So we're going to define so the first thing we're going to do is import a little function from a library called functools, which is going to make it easier for us to build decorators. Then to create a decorator, you just write a function that takes a function as its argument. Then we're going to say that inside the body, we're going to create another function which we decorate with wraps, and we'll get onto that in a moment. And it's going to take args and quargs. So we can pass anything we like, any way we like to this function. We don't really care. Then we're going to print that we've entered this function. Why are you complaining?
One bracket too much.
Ah, yes. Thank you. Then we want to call the function itself, and we reuse the star args and star quargs in order to be able to unpack the arguments as we get them in. And then we'll just print that it returned the result. And return it. Now, the next part that we need to do is make sure that we've created this wrapper function, but so it gets applied, we want to return that from the outer function. So, notice this, so we've got notice wraps on line, what is it here? Line 4. So this is a decorator that's built into Python, and that's quite useful because the problem with decorators sometimes is it can be difficult to trace them through. Here we're creating another function and returning it. So what you'll find is if we create our add function and simple syntax to create it, and then we just try calling, if we slide over to the terminal, using -i to execute things in interactive mode can be quite useful as well. And it's not working. It helps if you don't make syntax errors.
I believe in line 8 you also have too many curly braces.
Yes. So try this again. So now it's worked fine, and if we call add-on 3.4, where's this gone wrong? So the problem here is we missed off the star from the front of args.
Sorry, why is it star for keyword arguments?
So in Python you've got star args collects all the positional arguments up and packages them into a tuple. Then I suppose they needed a way to differentiate from it, so they just used star quargs.
So KW args is just a name, like you could
Yes.
be anything.
Yeah, you could call args and quargs anything you like. They're just other variables, and we're saying with star args, get all the positional arguments, package them up into a tuple, and put that into args. And with star quargs, get all the keyword arguments, package them up into a dictionary, and put that into quargs. So that means that we can call add with keyword arguments if we want to as well. So if we rerun this, add 3.4, we see calling add with 3.4 and it returned 7. I think that's what we expected. Let's see if we can add strings, because in Python that's something we should be able to do, and it works fine. But what if, say, I make a mistake and I decide I'm going to add 4 to hi? Now, we're not JavaScript, this should return an error, and it does do. And we get it quite nicely here that it tells us that it was in the add function and it then occurred in wrapper. So what happens if we omit this wraps decorator for a moment? Because if I reload this code, and let's just call help to see what we know about add. Well, if you look, it's given the name wrapper, but we called it the add function. So the benefit to using the wraps decorator, if I uncomment the right line, is that it will then, if we now call help on add, we can see that we've got the right name, we've got the right signature. That's kind of how we expect add to look rather than wrapper. So is that making sense to people?
Sorry, how does the log tie to the wraps?
Right, so if I come around here, so we've got the log function is the overall decorator, and then wrapper is a function that we're returning from it. Before, when we were just returning wrapper without the wraps decorator, it was saying, when we went for the help article, it went, okay, I want to get the name of the add the function contained at add, and because if we go back to the slides, the syntax of decorators, so we've got a function like this. This is what Python converts it to. So when we were before returning wrapper, we were just saying, I've got a variable add, set it equal to wrapper. So then when the help function was trying to go and get the name and the signature and all those things from the add function, it wasn't actually getting them from where we defined add, but rather from where we defined wrapper, and that was feeding through. So that's why it was so useful to have the wraps decorator, because that copies all that information through for us. You don't need it. You could do it manually, but Python's provided a way to do it nicely, so we might as well. So the next part is we can add it to different functions, and that worked, which is quite nice. But suppose I've got a massive program and there's loads of logging output, and I want to be able to differentiate, well, these are the maths things. Well, it's kind of useful to have a way of searching through your output, and you could look for called add with these arguments. But what if, for example, you don't know it's add you're looking for? What if you just want everything in the maths library? So logging some prefixes would be quite nice. So if we return to this example, then what we'd really like to be able to do, if we start from the end, we'd like to be able to say that the prefix for this is, say, 3 adds. So now this isn't going to work because it's going to go to Python, it's going to call the log function. Func will be a string containing 3 addition symbols, and it's going to go, what on earth do you mean? You want me to say that this function is like this function when that's not a function but a string? So the way we fix this is to add another level of wrapping. So let's add the prefix here.
Can you make it bigger?
Is that better? So prefix of, and let's say the default value is going to be a prefix of 3 hashtags, should be nice and easy to find. Now, within this we've now lost the original function we had, so we'll make another function nested inside. And okay, so we've got the decorator function that wants to take func. All of this will indent once, but now we need to return from the log function, we need to return decorator. So the goal here is that when we call it, log, called with the 3 pluses, will return for us a function that Python can then use to decorate add. Now, we'll see later a slightly simpler syntax for this, because at the moment we've got, 3-4 levels of nesting, which isn't the cleanest. We like to try and avoid that if we can. But so is this code making sense so far? But now we should probably put in the prefix. Now we've said that's what we're going to do. So we've got a way of passing it in, and we'll just add prefix, taking advantage again of the fact that we can pass arguments through into functions. Oh, sorry, the local variables get passed through, rather. So now, if we reload this, we can see we get our nice little prefix. And I can come in here, and I don't know, maybe we've got a subtract function that we don't want to give a special prefix to. And that's going to be fairly simple. And we can see that 5 minus 3 is returning 2, seems to be working fine. But do we really need these brackets here? I mean, if there's going to be multiple times where you want to call this function without passing a prefix to it, seems like those brackets are a little bit unnecessary, if you ask me. It would be nice if there was a way we could get rid of it. So, the next step we're going to do is also managed to get rid of some of the nesting, which will be quite nice. So, if we come back up to here, what we'd really like to do is say, well, log can either take the function or it can take a prefix. So we need to put func first because Python will just pass it in as a positional argument. So in order for it to get picked up, we have to pass it like this. Now, the catch is, when we pass prefix, we need to make sure that we're not accidentally setting func. So set that to none. Now the side effect is prefix will always need to be passed in by a keyword. So to make that clear to the user, we'll put a single asterisk. This has a similar effect to putting star args, but saying we don't care what args is. So we'll get func as the first parameter, then we'll collect in all the other positional arguments, don't care what they are, but everything that then follows this must be passed as a keyword argument. The other catch is we don't really need to ever say, because it's a decorator, we don't want to say, I'm calling you on with func equals this. So we'll make func positional only by putting the slash after it. And now, well, we can get rid of this step and put this back out. And when we call log here, well, that'll need to say prefix is that. And we can now get rid of the brackets. But what happens now is that if we try and call it as if we try and call it without passing func, we're just going to get wrapper that's not pointing to a function of any kind, and so we're still going to run into some issues. So we're going to add a little step in at the start that says if func is none, then, well, if we've not been given a function, we want to say this is the prefix you're supposed to use. Now here's a way of regenerating it when you have the proper function. So if we run up to the top, we're going to import another item from functools called partial, which lets you do, as the name suggests, partial function application. So basically we are just specifying here that what we're going to do is we're going to return a partial application of the log function, but we want to specify that when you do call it, make sure you call it with the prefix being set because we've provided one. So now if we come back down here, so if we rerun this, Python 3, then now if we call add on 3.5, we see 3.5, we get 8, and if we call sub on 3.5, we should get -2, and we can see that we get the default prefix, and we've managed to eliminate the brackets. So eliminating the brackets, that's a nice to have, but we need to pass prefix now as a keyword argument. Yes, there's a little bit more stuff, but equally, suppose we've got lots of arguments being passed to log. It's kind of nice to be able to say that we're specifying the prefix is +++, rather than, I don't know, if you've got something like, maybe you want to add something to change the name of the function. It's quite useful to be able to say that this is the prefix, this is the function name, etc. So the next step we're going to go on to is, well, decorators can be used to change functions. We can also use them on classes. So here we've got an example, and we'll go over to the code in a moment, which is creating a method, log methods, and this time we're taking a class rather than a function, but it's a decorator just the same. And now what we're doing is we're going to get all the items from the class, so that would be all the functions and things that you've defined within it, and loop over them, getting their name and what they are. And if it's a function, then I want to apply the log decorator to it. So if we jump over to see that in a bit more action, so log methods takes a class, and then we want to iterate over it, and if the current item is callable, then we're going to use this setAtta function, which lets us set an attribute on the class. And what we're going to do is we can say, well, on the class, the thing at name is equal to value passed through log. And maybe to make it a little clearer, we'll just print the name of the class when we do it. And now, like before, we need to remember that because the decorator is saying you've got class, my class is whatever, and it's saying my class equals log methods of my class. So we'll want to make sure that we return the class once we've modified it. So let's just say, for example, that this is in some kind of maths class. Then what we can say is, well, rather than having to log all of them individually, let's just log all the methods. And these should really probably be marked as static methods, because we're not taking self, we don't really care about the maths class itself. So we'll just mark those. And now we see that we've printed out add and sub just as we started. So that was when it was applying the log decorator to the class, it looped through and it found, oh, you've defined one method called add and one method called sub. So I'm going to now apply the decorator to those. And we see if we can do maths.add, say 6 and 8, for example, we can now see that it's applied our log decorator to that for us. Now, there's a catch to this, is that Python, this is how Python implements classes, it might not work, depending on what you're doing. You might need to be careful with static methods and class methods. For our case, it's worked, so we're fine. But there are scenarios where it doesn't work, so you've just got to be a bit more careful. Now, if we return to the slides, what if we want to log the attribute? So, I don't know, you've got a class of, say, a person, and every time we get their name, their age, any other property, we want to have a little message to say, we got their name, we got the person's age, and it was this. So, if we go through, so now what we're going to do is, it's going to be, let's start by making the class. So, let's say we're doing some networking stuff, and we've got some kind of network host. So this is a theme we'll be sticking with throughout. So we'll create an initializer method on it, and this is called whenever you create the class to set up all the instance variables that you've got. And we're going to take an address and a port, and we're assuming that the address is an IPv4 address, port is a valid port. And we'll set those on the class. Now, whenever the user accesses those, we'd like to know. So we want to be able to just do something along the lines of doing log attributes like that. So let's now go and make that function. Given it's a class decorator, what do people think might be a sensible name to call the parameter?
CLS.
Yep. And then the first thing we're going to want to do is to save the get attribute method of the class. So we're going to just grab that, and this is what the class uses whenever you try to get an attribute. So we're going to save whatever you've got originally. We're going to keep a copy of that so we can use it later. And then we're going to put in our own functionality. So we're defining a method, and because we're replacing the get attribute, we'd like to call it that. And get attribute, when it's applied to a class, takes self and name. So we'll make sure to call it that. And here we want to just call the original get attribute, passing in self and name. And we just want to put a little print statement to say, you got this name, we're returning the value. So put 1 in. And then, not forgetting they're trying to get the attribute, so let's return it to them. And then at the end, we want to override the get attribute method on the class and say that that's equal to our new get attribute function, and we'll return the class. So if we come down here, oh, I called it .py. So now, if we create a host, I don't know, let's just make it localhost. That works fine. And if I want to get the value of the port, we get a little statement to say, you got the port. And then similar thing for the address. And that's quite nice because now if we've got other classes, we don't have to try and recreate this behavior for them individually. Every class that we want to be able to log attribute access for, we can just do it here. So as you can see, a bit more abstract. Now, the catch with this is we don't get it applied to every subclass. So let's say we have, going back to the person example, the class person, log the attributes, great. Now you create a subclass of person, maybe student. We'd quite like for the student to still have the the new behavior, but by default that's not going to get, the decorator won't pass it through the inheritance tree. In our case, we're lucky, this would be, but if you're doing other things, it might not. So we'd quite like to be able to do log attributes to every class as it's created. And this is where we're going to start introducing metaclasses, which are quite a powerful technique when you know what's going on. So here, as an overview of the code, in fact, let's go in to here. So let's walk through it step by step. The first thing we need to do is create a class that extends type. And this is something we're going to keep coming back to as we go through it. Then we define a done new method on that class. And this is going to affect how not an instance of base meta is created, but we're going to use this to actually affect how Python creates classes later on. So we're going to say it takes its first argument is MCS, short for metaclass. Then we need to give it the name of the class, the base classes of the one we're trying to create, what we call the namespace. Now, namespace is just the body of the class. So you create a class that has a dunder init, maybe a Greek method, and so those will be contained within the namespace. And then here, showing a different way of calling it. Sometimes we call it KWDS, also for keywords. And this is because at a later date, someone else may take our class and say, we want to take some keyword arguments for the new function, so we accept them just in case they exist, so that way we don't crash Python. Now, the first thing we're going to want to do here is actually create the class object itself. Now, this is where it starts to get a bit brain melting, because I'm going to be referring to base meta as the meta class, and that's being used to create an instance which itself is the class. So rather than creating, when I say I'm creating a class, it'll hopefully become clearer as we go through the talk. So to do this, we're just going to pass stuff to super. We don't actually know how we make the class itself, but type does, so we'll let type do it for us, because if someone else knows, why do it yourself? And now we've got that class, before we return it, we want to make sure to log the attributes. And we'll just go and copy this function over from here. And this is another thing with decorators, because at the end of the day, they are just special syntax over functions. We can just call them as functions if we want to. We don't have to use the decorator syntax. Now, when you create a class that uses, in this case, base meta as its meta class, you have to specify that the meta class is base meta. So what's going on here is we're saying, I'm defining a class, and when you create me, I want you to use base meta as my meta class. Now, so you don't have to write that out every time, it's quite a common pattern where you'll create your class here, base meta, which will be the meta class, but then you'll create another class that has nothing in it other than the fact that it uses base meta as its meta class. So later when you're using it, say for my host, rather than having to specify that the meta class is base meta, because that's quite a lot of characters we're trying to avoid boilerplate, we just say it extends from base. So quite a bit simpler. But the catch is, anything that extends from base will automatically get log attributes applied. So take the address and the port like before. And set them. And if we come and restart this, we see that when we can create a new host just like before, and like before again, we get our little messages when we put it out. Now, you'll notice it's printed it out twice here. Anyone have any ideas as to why that might be? Right, so what's happening here is when we create the class base, that gets log attributes applied to it, which causes it to be printed out once. Now the meta class applies every single time we inherit. So when we create the class host, that gets log attributes applied to it. But if you remember when we define log attributes, if we come back up here, it gets the previous one and stores it. Now the catch to that is that when you want to, when we create the next one, the previous one's already referencing one that's printing it out. So that's something to be aware of, is that sometimes it might be more appropriate to use decorators, sometimes it's more appropriate to use metaclasses. So, going through it, so we've defined a class base meta, inherits from type, and then we use it as such. But there's, like I say, there's a few confusing things here. When we're defining the class base, it looks like we're giving it a keyword argument, and when we have base meta, that's extending from type. So let's take a step back and have a look at things. So type in Python most people get introduced to it early on and see, oh, it's a function that I pass in an object and it tells me what type it is. So if we say call type on 5, integer, I think everyone expects that. Now, the catch is type returns a value, and we've just seen that every value has a type. So that suggests to us that, well, maybe we could call type on int. So rather than calling it on an integer, say 5, we can call it on int itself. And it turns out that returns type. Now, that makes, if we stop and think a moment and say, okay, type of 5 returns int, type of int returns type, what does type of type return? And it turns out it returns type. So that's kind of where our line of inquiry finishes here. Now, what we're learning from this is that type looks like a function, but in reality it's a class. And it's taking advantage of a variety of different features to make magic work, basically. Now, what this means is all classes are, or at least all built-in classes certainly, are themselves instances of type, which kind of makes sense. If I want to check if something is a class, well, a class is a type, so we can do an instance check. You look like you're confused?
No?
No?
Good. Just steering into the abyss a little bit, yep.
So, how does Python actually create a class? If we have syntax like this here, then how does it go from this text to a class object itself that is an instance of type? Well, there's 4 main steps. The first thing is we need to isolate the body code, so that's the functions and things that are contained within the class. So pop that out to a string. Now, the next thing we need to do is create what we call the namespace, the thing that's going to contain these functions. And that means we need to have some kind of dictionary to store it in. This is where the metaclass first gets involved, and in a moment, and we'll get on soon to what metaclass is actually referring to here. But for now, we call prepare and we say it's a class of type greeter and it inherits from base. And that gets us the namespace. So we can start to see some of the things we can hook into within Python. So maybe we don't want a dictionary. Maybe we want some kind of, special dictionary that only lets us define a key once. So say, going back, you could only find the greet function once. Maybe that's something you want. So if we can change what metaclass is, we could provide our own implementation of prepare and then start to alter things. The next step is to execute the body. So we take that string from before and we now need to get Python to run it to provide us with some functions, and we pop those into namespace. So by the time we're done, namespace is a dictionary that's containing here 2 functions, and that's how we're storing the local variables, and it gets access to the global variables as well, because obviously if you're calling your function and you access the global variables, you need to get them from somewhere. Now, the final thing is perhaps the most important bit, and that's where we create the instance of type. So we get here that greeter is a type, and this is the other form of the greeter constructor. You can either call it with one argument, in which case it says what is the type of the thing you've passed me, or we can pass it with multiple, and it will then create a class with the name greeter inheriting from base and containing things contained within namespace. And so you can see how we can use this. You've got at the interactive prompt, greeter is a class. We can create it, and if we create it with world and call g.greet, we get hello world, which if we jump back to the how we defined greeter, it's kind of what we expected. So, are there any questions so far on that bit other what is metaclass?
Yeah.
Okay, go on.
Just that question. I
Oh,
you've also got to isolate the body.
Right,
I'm
so-
not sure if it's salvageable for me.
So basically, when we isolate the body, what Python's basically doing is it says, I've got a block of code that is some kind of class definition. I'm basically going to find the text that's contained within the body and just pull that out to a variable. So rather than having to do some magic, when Python's looking through your code, it just sees it as one massive string. So by the time we get to this point, Python needs to take out what we call the body of the function, so in this case the init function and the greet function, and takes their source code out, because at some point we're going to need to run that code to be able to have those functions. So then that's what we're doing when we're isolating the body. We're just saying the stuff that's contained within the function, the literal source code that you're using to define that, pull that out to its own little string, because if you want to execute the body of the program, if you want to, when we later need to execute the body, we just need the contents of that, the source code of that, the contents of the class. We don't really care about things outside the class when we're trying to create the class itself, if that makes sense. Then namespace makes sense somewhat.
I don't know what metaclass is. I don't know what .prepare is. I don't
Yeah, right. So metaclass for the moment is a variable. We're going to get on in a minute to say what that actually is. The .prepare is a function on metaclass, which is returning a dictionary that we're going to use as the namespace. So it's just a function that takes in the name of the class that you're making and any base classes it might have, and it then just produces some kind of dictionary. You might do some fancy thing where you want to put things into that dictionary already based on the information we have. Usually we just return a dictionary of some kind. Then to execute the body, we take that source code that we extracted earlier and we pass it into the exec function, which is built into Python. It lets us take in Python source code and run it. We'll get onto safety of exec at a later point. This part, fairly safe. Python's doing it for us. It's got to run that code at some point anyway. So Python using exec to make Python work is, I think, allowable at the very least. So does this make sense mostly? And then this final part here, it's probably best to think of type as a class like any other. It's got a constructor. We can create it from some arguments. And that's all we're really doing here. We've done the fanciest bit. We're just saying, I want you to make me an instance of type called greeter, got these as base classes, and it's got this as for its namespace attribute. Yes?
One question, where's base coming from?
This is just an example for this. It could be anything. If you don't have any base classes, that would be an empty tuple. It's just so it was a bit easier to trace through where things are coming from. So is that making a bit more sense?
A bit, yeah. Thanks.
So now to the question that we've been wondering, what is this metaclass variable? By default, when you create a class, it's just type. So type under the hood is providing the prepare method. It's providing all the functionality we need to create it. But it's the way to think of it is kind of like a keyword argument. So we can provide our own values later if we want to, and that's what we saw when we were doing the log attributes before. And when we're creating a metaclass, we either typically override the dunderNew method or the dunderInit method, because typically the point of a metaclass is to alter how the type is being created. So does that starting to make things a little bit clearer? I think the other part is it's all quite abstract at the moment. When we get onto writing the metaclasses and playing around with them more, things should start to become a bit clearer. So basically, metaclasses get given information about the class definition when you're creating the class itself. They can tweak it, they can inspect it, they can do different things based on its values, and then create some kind of class that should probably somewhat resemble what was passed in. They don't have to, but if you want people to understand what's going on, they maybe should. Like, when creating a class, I could say, oh, you know that class you've made? Well, actually, my class is just an integer 5. I probably shouldn't, because that's going to confuse loads of people when they see class my class and think, why is it 5? Why is it not a class? But you can do whatever you want. So they're kind of similar to decorators, that they're taking in a class and then tweaking it, producing a new thing. Now, the main difference is that metaclasses go through inheritance in the way that decorators don't. So if you use a decorator on one class, its subclasses aren't going to be decorated unless you've done something that actively affects the inheritance. Nothing new is going to change. Metaclasses get applied to every single class in the object hierarchy. So if you do something wacky in the metaclass for one class, any children of that will also get that applied to them. So just briefly, we've mostly been wrapping and rewriting things, and we've done decorators for functions and classes. Metaclasses can be used to mess around with inheritance. We've not quite seen their full power yet, but just sort of that it's a thing that they can do. So now let's move to a slightly more involved example, and we'll be running with this for most of the rest of the talk. It's quite a common one, and it involves an awful lot of boilerplate. We're dealing with structures. Now, I should point out that for this talk, we're going to assume that the data classes module doesn't exist, because it invalidates this entire talk and the entire thing that we're building now. But it's a good example to demonstrate and build out the tools that you could then use for many other things. If you've not heard of data classes, do go and check them out, it is quite useful. So here we've got two classes, point and host, and they're quite different from each other at the moment, but in just this capacity they're not particularly useful. Let's say we want to be able to print them to convert them to strings. We need to add in the repr method. That's what one of the two methods that Python uses for converting things to strings. Now, the problem with this is a lot of that method is the same. The only real difference is that for point, we're printing out the fields of point, and for host, it's the fields of host. But actually thinking about what that code is doing, they're basically two identical methods. So that's some boilerplate. And now we want to be able to compare points to points, hosts to hosts. And again, this code, I realise it goes off the screen a bit, but here we're just checking the Z component of the 2 points, checking the ports of the two hosts. And they're practically identical. So it would be nice if there was some way that we could abstract this out, because those methods you could generate entirely. You don't need to make your own, or to make them identically for each. So the solution to this, we're going to start off with something simpler, and gradually as we go on, we're going to keep building and building and building until eventually there should be almost no boilerplate. And depending on how long we've got at the end, we might start to make things a little bit more abstract, but again, depends on how much time we've got. So if we switch over to the code demo, what number is this? Number 3. So we're going to create a class called structure, and this is just representing any structures we might have, and we're going to give it a class attribute called fields. And this is how we're going to start to be able to remove some of the boilerplate. And it's got an initializer, which takes star args. And the first thing we're going to do is we're going to check that that you've passed in the right number of arguments. So check that the length of fields, if it's not the same as the length of the args, then we're just going to raise a value error and say wrong number of args. Just because otherwise, if we don't do that, and say, let's say with the host, you try to create a host with an address and no port, we don't have any defaults, that's going to go wrong. Or you try and create a point and decide you want to work in 4 dimensions. Our point does not support 4 dimensions, we're just going to not count that final part. So then the final step of this initializer is we're going to iterate over the fields and the args together in step, and we're just going to set on self, we're going to set the field to the argument. So when you create, say, your host, we're going to say the address is what you provide in the spot for the address, the port for the port, and so on. And so if we create our point, and it's worth noting, for the moment I'm not going to be implementing the repr and equality methods.
You're missing an S in line 14.
Yes, fields, not field.
Sorry, what's that syntax where you have like on line 14? What is that? I've never seen.
Line 14.
Mm-hmm.
So basically, it's creating a tuple. It's just Python lets you drop the brackets if it's clear what it would be.
Mm-hmm.
So we'll leave the brackets on for that one. Then we're going to create our host structure. And for this one, we're going to define that fields is a tuple containing address and port. So again, this is fairly simple. And already, even just compared to the initializer, we've managed to strip down a lot of what really was boilerplate code. Because, well, when you're creating a point, of course you want to set the x to the x they provide, self.y to y, self.z to z, and so on. And the same thing with the host. It's kind of, why do we have to redefine that behavior for every class if that's always what we're wanting? Now, the catch to this is if we go and demonstrate it, so now we can create a point P takes 1, 2, 3, and we can get x, y, and z nice and easily. The problem with this is, let's say I want to create a host, and I want to specify that, well, just to make it clear, the address is what we're setting to that, and this is the port. So I want to pass in by keyword arguments. Well, then Python gets confused because if we look at the initializer for the structure at the top, it doesn't take any keyword arguments. Why are you passing keyword arguments? And similarly, I'm going to import, if I can type, I'm going to import a module called inspect. And this, as the name suggests, this lets us inspect functions and things to find out more information about them. And one of the things that we can do is get the signature of things. So when I'm constructing point, we kind of want to say this is point constructor takes an x, a y, and a z. But it just takes star args. And similarly, if I were to go to help on host, again we see the constructor just takes star args. It's not particularly helpful. So it would be quite nice if we could modify this so that those produced the correct value, so you knew what you were dealing with. So what we're going to do is use the inspect module and basically say, you don't know what the signature for that is, but I'm going to tell you. So first thing we need to do is import some things from inspect. And because we're dealing with the signature and we're saying what the parameters are, those are the things we need to import. And this is kind of where it starts to get a bit more interesting. So we'll define a little function here to help us, say make signature. And that's going to take some fields. And then it's going to return for us a new signature. And the signature contains a list of parameters. So each parameter, the name is something we're going to come on to, and we say that it can be passed either positionally or by keyword. So that way the functionality we tried to get earlier with the host that broke works. And we're going to get the name just by iterating over the fields. So people are fine with that so far?
Names not.
When you get to the for name in fields, it should stop moaning that it's not defined.
Okay.
So this is a list comprehension. So we're just saying loop over everything in fields, and then for each of the names in fields, I want you to create, basically append a list item created from that parameter.
The thing about this, is it conceivable that you could accidentally put in the wrong signature for the function and then your inspector would be telling you misinformation about the parameters?
Yes, although what we're going to do is we're going to make sure this is enforced when you're calling the function.
Okay.
And it's when you define the class is when we figure out what the signature should be.
Okay.
So long as you've defined your class correctly, it will work correctly. If you've not defined your class correctly, well, if you defined it wrong before, it was still going to not work.
Yeah. Okay.
The old phrase of garbage in, garbage out. So now what we're going to do is we're going to say, well, instead of taking the fields from the structure, it's going to have a signature, which will default to none, but you're going to need to overwrite it later. So that's no longer applicable. And the first thing we're going to do is make sure that the signature is not none. So if it is, we'll raise an attribute error and say must define, say that you need to define the signature, otherwise we have no clue what's going on. And the next thing we're going to do is we're going to take advantage of the fact that the inspect module, not only can it look at things and find out information for you, it can also help you to enforce that information. So we're going to bind the arguments that you pass in, and in fact that also can now take keyword arguments, and we're going to bind them to the signature. So what that means is we'll get out an instance of bound arguments, and that will correctly map the signature that we say it's supposed to have will be correctly mapped to the arguments they pass in. If you pass in too many arguments, too few arguments, keyword arguments that don't exist, the signature will take care of that and will tell the user appropriately. And now the final thing is to iterate over those arguments and set them like before. It's just this time, rather than having to combine them ourselves, we're getting Python to do it because Python knows how to do it properly. So now we've not had to change anything to our user code. We do have to change one thing, and that's replacing fields with the signature. So if we rerun this and we say want to create a point and say the user tries to do it with 4 parameters, it tells us too many positional arguments. If the user tries to create a host, and say specify support by keyword, that now works. And importantly, if we ask for help from the point, we get the appropriate signature. And the same thing will happen with the host. So now if someone's trying to figure out how to use your library, they get useful help info. So the downside to this is we've lost access to just what the fields are. You've now got to go through the signature and try and get the arguments, which would mean if we were to generate our repr and equal methods, it's now harder. So what we and the other thing is, well, if we look at this, every time you set the signature, it's always going to be set to the results of a make signature call. It would be quite nice if we could replace that, because if you've always got to do it, that's boilerplate. So instead, what if we could just go back to specifying the fields, and then our metaclass creates it for us? But the catch to that is, well, we could regenerate the signature in the structure initializer. But the other thing is the signature never changes, so we kind of want to generate it once and be done with it, because if you're having to generate it every single time, well, that's quite wasteful, really, if you could only do it once. So there's 2 options that we're going to investigate here. We could either do it with a class decorator, or we could write a metaclass to do it. 2 different options, and we're going to explore both of them. So first, we're doing a decorator, and here we're defining it as a class. We've seen before how to define a decorator that takes arguments as nested functions. Now, because the dunderCall method, perhaps unsurprisingly, makes instances of a class callable. So under the hood, a function would look something like this. Granted, it's a little bit special because saying a function is a thing that has a function on it, how do you define that? So that's where the implementation of Python starts to get a little bit more abstract. But the nice thing about this is it's a little bit neater than having to nest lots of functions within each other. We can just say it's a class. When you create me, I take some fields and I'll save them. And then when you call me, I'm going to make the signature and apply it. Now, another catch with this is you'll notice I've named the class in what we call snake case. Now, normally in Python, you'd name classes in Pascal case because that's what we're taught to do. Now, the thing with this is there's 2 different ways of thinking about naming things in Python. The first one says you name things for what they are. If it's a class, you use Pascal case because that's what we use for classes. If it's a variable or a function, snake case. It's a variable or a function. And constants in shouting snake case. Now, the other idea is, well, we could call things based on what they are, but some things pretend to be something else. So like you might have a variable that is acting as a class. Or in our case here, you might have a class that's really trying to be a function. So the other school of thought is name things as what they're trying to be. And the benefit to that is that when the end user is using your code, they don't really care how things are defined or what they are. They care what they're supposed to be using them as. So that's why I tend to go with the latter approach. So the other option for generating our signature would be to do it in a metaclass. Now the benefit to this, and the real big benefit, is that it will happen every single time you inherit. We don't have to reapply the decorator. So overall, That's probably what we're going to go with. So let's go and put that into our code. So the first thing to do is to create a class structure meta, and remember metaclasses need to extend from type. Then we want to define a done-to-new method that's going to take the metaclass itself, the name, bases, namespace and keywords, and then the first thing we need to do is instantiate the type. So as will become routine, we say the class is equal to handoff to type to create it for us, because type knows what it's doing. And then we say, well, the signature of the class we're going to make a signature from the fields of the class, and then we return it. So this, on the simpler side as far as metaclasses go, we just go through, create the class itself, apply the signature, and return it. Now, do you remember how we say structure is going to use structure meta as its metaclass?
Saying metaclass equals.
Yes. Now we want to replace, yes, so we want to replace signature, because that's now being defined for us in structure meta, and just say fields defaults to an empty tuple. And now, well, signature won't be none. It's guaranteed to have been defined for us by the metaclass, so we can get rid of that. So we've managed to actually trim down our structure class a bit by doing this. And these will return to being fields. And now, if we come back to here, we say that host is a host. And that works fine. But importantly, if we get the help for it, we get the right value, we get the right help still, but we've not had to go through and create the signature every single time. So, does that mostly make sense to people? So, what are the cases that we would use the decorator versus the metaclass? So especially in this case, the decorator definitely looked simpler. It was much simpler to implement and in a way simpler to use. However, it still wasn't storing the fields for us on the class itself. The fields were being passed to the metaclass. We could have applied them, but then you're still kind of doing things in two different places. And the declaration of the fields was somewhat detached from the class. If I go back, let's go back to the code and just quickly create an example of how and just briefly show how you would create that. So what we were doing before was it would say, look, something along the lines of add signature, and then your class would have been empty. And to me that looks just kind of a little bit odd to say that, well, we're defining the fields outside of the class when in reality they're a part of it. So that's why to me it makes more sense to go with the metaclass in this instance. It just generally looks at least a little bit clearer. So because of that, I think the metaclass is probably a reasonably sensible way to go, and it has the other benefit, as we saw, of being passed through the inheritance hierarchy. So the catch to this is, at the moment, we've got some issues inherent to Python still. Address, well, we said that's an IPv4 address, and last I checked, the integer 42 is not an IPv4 address. Similarly, the port probably should be an integer, not a complex number. So some of you might see where we're going with this. If it waddles like a duck, if it swims like a duck and quacks like a duck, surely it's a duck. Yeah, thanks, Dali. Maybe not everything that acts and looks like a duck is a duck. Maybe we should just use Rust. Would certainly get us out of these issues. Well, while still staying in Python, we can use the property decorator to work our way around this problem. So what we're going to do now is let's copy 3 to 5. So inside, say, the host, and we'll just apply this to a host for the moment because it's going to get a little bit tedious. So we're going to have got a property which is port. Port is going to be the simplest one to implement this for. And okay, if you're getting the port, we'll return a variable underscore port.
Sorry, is that in the right club?
Yes, under the host class.
Oh, sorry.
And then we're going to create a setter for port and say that that takes a value, and we're just going to check that value is an integer, and also, and then if it's not an integer, we want to raise a type error. And in reality, port should probably be positive. I've not yet come across networking code where I get to use -5 as a port number. So value, sorry. And then finally, if those checks pass, we're going to set underscore port to the value. Now, that's got us some nice type safety. And yes, the user could work around it by setting underscore port directly. But in Python, there's a convention that if a name starts with an underscore, that's for the internals of the class. So pretty please don't touch it. But the problem is, if we look back at this, didn't we say we were trying to get rid of boilerplate? If you ask me, that's an awful lot of boilerplate, because the setter method is going to be basically identical for the getter method is basically identical for every single attribute we're going to have. And even with the setter, well, anything that needs to be, that we're saying should be an integer, that if instance check will have to be there. Anything that shouldn't be negative needs a value check, and then everything's ultimately going to get its value set. So whilst it's safer, there's, like I say, loads of duplication, and it would be nice if we could work around this somehow. And this is where the final part of descriptors come in. So under the hood, this is how Python actually implements properties, and like most things in Python, if Python can do it, so can we. So this is a very simple descriptor. We define this is the most generic descriptor rather. We define 3 methods on it: get, set, and delete. And get is called when we try and get the value, set, setting, delete, deleting. And supposing we've got a descriptor, having a look at it, you can see how the function calls get mapped. And under the hood, this is how class methods and static methods are also implemented, because when you call it, say we called foo.x on the line right here, that f would be none if it doesn't exist. And so the class method is able to say, f is none, I don't care, I'm just going to give you the class. So, a slightly more involved descriptor that's actually doing something, which we'll go over and write the code for. So we create a class, and for now we'll just call it descriptor. And we need to take some kind of name so that we know what the member within the class that we're actually taking control of is. So we'll store that. Then if we want to get the attribute, so that takes the instance that we're trying to get it from, and it takes the class that we're trying to get it from, and we're going to say these have to be passed positionally.
Understood that.
So then when we're doing this, well, if the instance is none, that means we're being called on a class, and so it probably makes sense to just return the decorator object itself. Otherwise, what we're going to do is we're going to peek into the instance and fundamentally into the dictionary that the instance is made of, and we're going to get the thing that we're pointing at. Then we have set method, which takes the instance and this time the value you're trying to set it to. Again, pass that positionally. And we're going to just set the value. Similarly for the delete method, we're going to get self and instance, and we're just going to delete it from the instance dictionary. So overall, quite a simple descriptor. Now, the thing is that our get method is fairly standard, and so Python can actually identify, oh, you're making a descriptor. Well, in that case, you don't really need to define that method because Python's smart, it can work it out for you. So we can get rid of that method. And similarly, if we're going to be using this to describe the fields of a structure, given the nature of structures, the fields probably we're not going to want people to be able to delete them. If you said a point contains an x, a y, and a z, why would we want to be able to delete y from the structure? So instead of deleting it, we will raise an attribute error and just say that we can't delete it. So are there any questions about this so far? In which case we'll move on. And I think because we've still got quite a few slides to go, rather than trying to continue to the end, we'll look at how we use the descriptor, and then I think if we call it there for today, and we'll look at revisiting this and continuing it in a later session. So we're just going to recreate the host class here.
Sorry, is there any point to implementing set? Does Python not do that for you if you give it default behavior like that?
I think it might be able to do it for you,
Okay.
but what we're going to do in the next session is come back and implement subclasses of descriptor, and so we want to make sure we've got that base behavior there. So those subclasses will just be responsible for checking things and then calling up to the parent. So like we'll have one that does type checking and says, if it's not the right type, throw an error and complain, otherwise go to my parent and do the rest of it. So that's why we've put it there for now. So we're going to take the fields and then address is a descriptor, and we're pointing at the address field in the dictionary. And similar thing for port. And if I just go and borrow the structure classes from the previous example, then we can run this just to check we've not broken anything. And if we create an instance, we can see that it's all working properly and we can still get things. And if I try to delete the port from our host, it won't let me. So does that all make sense to people?
Yeah.
Oh, yeah.
It doesn't do any value checking or anything.
Not at the moment. We're going to come back to do that at a later session because we're out of time and about halfway through the slides. So we'll make that another session in a few weeks and we'll let you all know when it's coming back on.
Wait, how many slides did you prepare? You said you're halfway through.
If we go back to this, oh no, the progress bar is there.
Okay, right.
So do we want to try and power through the rest of them, or should we leave it there for
I'd say
today?
it's 7:30. Give it
Yeah.
a rest.
We'll come back and maybe do a 40-minute to an hour session at some point in a later week
Okay.
and finish this off, and that way we'll definitely have time for the example that takes things too far, which is always fun.